intro and all the rest of it, yeah? Okay,
sure.
Super. Okay, well, thanks everybody for coming for another SNAPP seminar. This week we've got Dan Russo. Dan Russo's joined the decision, is in the Decision Risk and Operations Division of Columbia Business School. He's where he's associate professor. He's also previously spent a year at Northwestern's Kellogg School of Management, and prior to that he was at Microsoft Research, New England, as a postdoc, and prior to that he did his PhD with Benjamin Van Roy. His interests are on the intersection of statistical machine learning and sequential decision making, with contributions to online optimization and reinforcement learning. Dan's just told me he's come back from a good stint doing RL with reinforcement learning with Spotify, which I find great. And he's done a lot of fantastic work in reinforcement learning, temporal difference learning, information-directed sampling, and also more recently policy gradient algorithms. But that's not what he's going to talk about today. He's going to be talking about multi-arm bandit experiments, and specifically adaptivity and confounding in those. So great, Dan, it's great to have you, and looking forward to your talk.
Thank you, Neil, for that introduction. And thank you to the organizers and more broadly for the invitation. Today's talk is going to be touching on the subject of multi-arm bandit experiments, which is something I've thought about for many, many years, almost my whole career, I guess. But I'll be kind of revisiting the topic and stressing issues that were never really the central focus in my mind previously. Kind of my partner in this is Chao Chin, who's a PhD student at Columbia Business. Okay. All right. So I think many people in our field are interested in this set of questions around how to learn efficiently in interactive environments. Okay, so what do I mean by that? There's been this explosion of data sources that are, in a way, interactive, where if you kind of sit down and think about how to model them, they look a little bit like this picture up at the top, where the decision maker is trying to learn how to take actions in order to attain some objective, say here measured by whether you get high or low reward. And a dominant feature of these learning problems is that learning requires some kind of efficient trial and error, efficient experimentation. Because really you're only getting feedback on the kinds of actions you actually test out. So in response to the explosion of problems that actually look like this in the real world, there's been an explosion of academic literature on bandit learning algorithms and reinforcement learning and so on. Okay, and here's just a small sampling of different kind of application areas that have been modeled using this sort of framework. And if you go through and look at published sources from some of the leading tech companies, you'll see that many of them have documented success using different kinds of bandit algorithms. All right. But despite this, there's something that we should take seriously. Is that nevertheless, classical randomized controlled trials are still the gold standard. They're still the most common thing that's done in practice in many, many years. Now, what do I mean by a classical randomized controlled trial? I mean that the way in which measurements are gathered is this sort of simple way. We have a finite set of treatment options of arms in a bandit problem. And at each moment in time, when assigning a treatment option to a individual or a user, we do that just by picking one uniformly at random. Okay. All right, now why is this simple, naive thing so dominant in practice? Well, certainly some of it is just institutional resistance to adopting the newest, hottest thing. But I think we should be humble here and instead take seriously that maybe there are concerns underlying the ubiquity of classical randomized control trials that are not well captured by the way we usually write down multi-arm bandit models. So in this paper and in this talk, I'm going to try to take seriously some of those concerns and write down a new twist on bandit models where for an algorithm to perform well in certain instances of those problems, it's going to need to exhibit robustness to delay, delayed feedback, and robustness to something we're going to call non-stationary confounders. Now, to treat this class of problems, we're going to propose an algorithm we call deconfounded Thompson sampling. It is taking a kind of foundational algorithm, Thompson sampling, and making a small but critical adjustment to how it's usually employed. And just so you think about the problem the way I'm thinking about it, in the back of our minds, I guess, we're trying to not just treat the kind of restricted model that we write down, but come up with a way of treating that restricted problem that seems likely to generalize to many other problems that aren't those we specifically wrote down. And modifying a flexible approach of treating the problem seems like the right way to get that done. All right, and the last piece of the talk will, it could either be a lot of time or a little bit of time, depending on how quickly things go. I'll talk about two different kinds of theoretical guarantees we can give to this algorithm. So one result is stress testing the performance of the algorithm in hard non-stationary instances, basically in settings where a randomized control trial is very hard to beat. A second set of results is going to stress test performance in a model that looks, in instances of the model that look kind of tailor-made to bandit algorithms, and see whether we preserved the kind of asymptotic efficiency guarantees we like to see in this sense. Okay. So this part of the talk is an outline and a teaser before we get into those three. So here's a bit of a teaser. What is the core tension we're focusing in on? All right. So here, let's there's a tension between, I would say, two kinds of concerns. So one concern, and the classical concern that's the focus of the multi-arm bandit literature, is efficiency. So efficiency in that literature is attained through adaptivity. What do I mean by that? If you look at this picture, say here in the bottom left, there's three possible treatment arms, arm 1, 2, and 3. And you can see that arm 2 is the best one. And arm 1 is competitive. Arm 3 is junk. Now, both from the perspective of getting high reward and from the perspective of trying to focus our measurement effort where it's informationally useful, what we would like to do is not spend much energy on arm 3. Okay, it's just easily ruled out. And what multi-arm bandit algorithms potentially do is figure out early on to focus effort on arms 1 and 2 and not arm 3. All right. And this way of zeroing in on the competitive part of the decision space can give critical efficiency benefits. All right. Now, this goal of efficiency is at tension with a driving motivation behind classical randomized control trials. And that's what I'll call robustness against exogenous non-stationary confounding factors. All right. So what's happening in this experiment is that we're experimenting across time. Right? Across time, we're deciding how to allocate measurement effort. That's the key to adaptivity. But in these pictures, coinciding with our experimentation is a non-stationary kind of exogenous non-stationary factors that influence the performance of our treatments. Right. Now, in the picture on the left, this is sort of a small deal. And in the picture on the right, the variability in due to exogenous factors is really much bigger, having a bigger impact than which treatment arm you pick. All right. So effectively, what randomized control trials do is they guard against this by fixing the chance that they measure an arm in each period, so that there can't be a weird correlation sort of between when you pick arms and the non-stationary process. Whereas adaptivity risks breaking this robustness because there's a pattern in when I've played an arm across time and when I've tended to play it could coincide with this exogenous variable. I could mostly play arm 1 in the beginning and mostly play arm 2 at the end. If I'm not careful, that leads to confounding. Okay, so that's a teaser. With that teaser, what I would sort of walk away with is a feeling like, okay, well, let's just give up on adaptivity. If there's only 3 arms, let's just play all 3. What's the big deal? And this won't be a big deal for this talk, but as a bit of motivation, it's worth mentioning that if you gave up on adaptivity, you're giving up on a huge part of the literature. You're giving up on major goals in artificial intelligence. You're giving up on reinforcement learning. Because in many of those problems, the decision space is enormous. And for example, in reinforcement learning, the only way that we can efficiently learn to find the optimal policy in a Markov decision process is by, over time, quickly zeroing in our experimentation effort on the part of the policy space that is relevant. All right, you can't just try policies uniformly at random. All right. So the last bit of a teaser, more of a teaser for theoreticians and then connoisseurs of this area, is if you're thinking only about the algorithms we'll talk about in this paper, Thompson sampling and upper confidence bound algorithms, there's a sort of an unsatisfying gap in the theoretical literature. So a common sort of meta lesson from some early papers on this subject, including one by myself, is a sort of feeling that Thompson sampling is like a bit of a randomized approximation to upper confidence bound algorithms. All right. And on the right, you're actually getting a sense that Thompson sampling is incurring a substantial penalty relative to UCB for the fact that it's randomized. Okay, so the regret bounds are worse. And if you open up what I think will become kind of a canonical textbook on this subject, right at the front part of the chapter on Thompson sampling is asking readers to ponder whether the randomization in the algorithm is a good idea, what the price of that randomization is, and what its benefits would be. Okay. So one sort of interesting nugget in this paper is in the hard non-stationary instances of our problem setting, deconfounded UCB, so this UCB analog of the Thompson sampling algorithm we propose, fails completely. All right. And the Thompson sampling version succeeds. So there is suddenly a division between what these two are capable of doing. And for both the intuition and the proof, it seems that the randomization in the algorithm is sort of critical. So a lot more work is needed here, but it seems that this is starting to get at the question raised in this teaching. All right, there is the sort of teaser and kind of a broad overview of what the paper is going to have as a contribution. Now, with that, let me dive in more specifically to the model. All right, I said that the model is going to try to take seriously the concerns underlying classical randomized control trials. So I'm going to formulate a problem that in many ways resembles a contextual bandit problem, but it's going to look a little different to try to align with the way maybe something like an A/B test looks like at a usual tech company. So here is a kind of prototypical A/B testing problem. I'm taking as a motivation here, I'm grabbing a part of the Spotify app. I guess Neil mentioned at the start that I do some work with Spotify. This is not a problem I've actually worked on, and so I'm more speculating here, but it's meant to capture features of a prototypical A/B test. Okay, so what is this? At some point in the last couple of years, Spotify rolled out this new feature. It puts shortcuts up at the top part of the app. And whenever you do things like this, you make changes, you run A/B tests aimed at evaluating product changes. Okay. And there's many possible choices that we might make about how to set up this new feature that picks personalized shortcuts for you up at the top. We could pick a different UI. Okay, we could choose to have 4 icons here rather than 6. We might choose to have 8 rather than 6. Right. Now, another choice is which machine learning model feeds in the recommendations that go up at the top. Okay, so usually what happens is there's some classifier trained on a particular definition of the label for a success or a failure with that individual recommendation. And people come up with different definitions of the label and different definitions of the training data and so on. Okay, so between the cross product of these two decisions leads to a bunch of different options we might deploy out into the future. Now, what happens during the experiment is that when users arrive, they are assigned particular treatments. And we measure some kind of holistic, not something like micro, like which card they click on, but a kind of holistic reward capturing something about whether they've had a desirable behavior on the app following this intervention. So this could be things like overall, how much did they use the service? It could be more measures that are targeting really the intervention, like what percentage of streaming happened from the homepage rather than forcing the user to go to the search bar to find the content they want. Okay. Now, in addition to the actual reward, we are observing a bunch of contextual information about which user showed up, that the day and the time of day they showed up, whether there's a promotion running that actually goes on top here and may mess with the experience. We observe details about the user, things like how much they usually use the app. And we have information on their previous 10 minutes. Okay, which could capture things like whether they're using voice commands, which again would really mess with the interpretation of what's going on. All right, so I want to make two comments here. One is that we don't need to run an experiment to learn about the context. Okay, the contexts are something that we could just grab all the data on the service for the past, say, 3 months and see who's arriving and what are their usage patterns usually look like. okay? You don't need to, the experiment is run only to evaluate the impact of the treatment decisions, not to learn about who uses the service. Now, the second factor I want to mention is that the contexts explain a lot more probably than about users' behavior than whether they have 4 cards or 6 shown. All right, so the treatment arm has kind of a small impact relative to the overall variability in the system. All right. Now, the last thing, and I'm sorry, this takes quite a lot of slow motivation, I guess, to write down a slightly different model than one is used to. But the last bit of motivation I want to draw from here is you'll notice that in say a contextual bandit problem, my usual objective is to pick the best arm for that user in this given context. Okay, so based on the user's previous 5 minutes of listening, I want to figure out which algorithm to use to fill the cards and whether to use 2 or 8 or so on. That's the usual contextual bandit model, is they're changing the UI on the basis of the user's last couple minutes of usage. That would be a pretty annoying experience if whenever you flipped around the app, the UI changed on you. And so that is not what they were actually trying to learn. All right. Instead, the decision that is trying to be learned here is something that's going to be standardized across the population. We fix which machine learning model to deploy in production. Then we stress test it in the engineering checks, and then it gets deployed to everyone. Okay. So if you spend your life reviewing contextual bandit papers and sometimes writing them, there's some cognitive dissonance that sets in when you realize that the goal might not be to maximize the reward in the current context, kind of ignoring all else. Okay. But if you go look around the real world, then find many of the examples you're used to actually involve quite a lot of standardization and not personalization. Okay. So just to give you a few hints at this, we talk a lot about personalized pricing in our field, but Amazon, as far as is documented, does not use personalized pricing, right? And they tried it, they got caught using it once in some experiment, and there was a huge backlash. Haven't tried it since. Usual leading companies like McDonald's, part of their value proposition is that any store you go to, you're going to get the same experience. Okay, so they're offering consistency across contexts as part of their value proposition. Now, if you look at mass manufactured goods, those tend to have consistency across consistency in the product as a way of reducing operational costs. So there's other places where there's ethical or legal constraints. Really, there's many reasons why you would want the policy you deploy and the actions it picks to be invariant to parts of the context. All right. Now, whenever there's some degree of standardization in the problem, is when some of the issues in this paper come to bear. And so we'll focus for kind of convenience on an extreme point of the formulation, where, like that Spotify experiment, we want to pick a single arm to deploy in the population. So it's the most standardized decision. Everyone gets the same action in every context after the experiment is run. All right. So here, starting in on the formal model, our objective is in running an experiment is to learn which treatment arm to deploy throughout a population. If we had perfect knowledge, we would make this kind of the efficacy of each treatment arm in each context. We would make a utilitarian choice, picking the arm with the highest average treatment effect. So here is notation. I'll let I star denote the unknown best arm. And it's the arm that maximizes the average here reward drawn across weighted by how often contexts occur in the population. And this inner product here is sort of a standard, sort of a canonical model in the Bandit literature. I'm assuming that rewards are the inner product of a known feature vector associated with the context and an unknown parameter vector associated with the arm. So now in this model, there's going to be two ways in which prior knowledge available before the experiment starts, enter. One is, I'm going to think of the population distribution over context as being known. All right, this web service can look back over the past 3 months and compute how often contexts occurred in their data. They don't need to learn that with 1% of the users who are participating. The second way in which prior knowledge is entering in is through a Bayesian prior. So here in something like the pricing example, having a prior over this vector of parameters tells us kind of even before the experiment to learn to price this particular good here starts, we have some initial understanding of which segments of the customer space are more or less sensitive to pricing. Now, kind of the last bit of the model, I'm going to tell you about how the experiment is run and then what's done after the experiment. So during the experiment, we're going to, in each period, observe a context, pick an arm to measure in that context, and observe a noisy measurement of the quality of the reward offered by that arm in the current context. Now, one slightly non-standard thing is for part of the paper, we'll kind of get for free an ability to deal with delay. So delay says that the kind of restricts how adaptive an algorithm could be by constraining the choice of arm at time t to depend only on rewards observable up to some number of periods ago. Now, running that experiment, kind of at the end, let's say we had run the experiment for capital T periods, then we've generated a data set, which I'll call the history HT plus, that could be used to make a choice at the end of the experiment. And what we'll really be interested in is something Stefan Wager calls the utilitarian regret. It is measuring the price of unresolved uncertainty by measuring the gap between the average reward we'd earn by deploying the true best arm across the population. And here, the average reward we'll earn by deploying the best arm we can pick given limited information across the population. Okay, so that is sort of the broad setup for the model. Where I'm about to go is to show you that something that surprised me at first, which is that there's going to be a real divide between the types of algorithms we may want to deploy and the problems we can model, depending on whether we restrict contexts to be IAD or allow them to be highly non-stationary throughout the course of this experiment. Okay. So where I'm about to go is to show you what happens to this problem when you allow the context to be non-stationary. But maybe this is a good moment to pause and see if there's a round of questions.
Yeah, this is Alan. I actually have a question right about what you said, which is the non-stationarity. So we know the context weights, right?
Yeah.
And but this is a stationary distribution of the weights, or if we prefer sort of a time average of the weights.
Yeah.
but they may have correlations among them that we may or may not have measured.
Got it. Yeah, I think that we know the time average of the weights over a very long time, say over a month, but we were running an experiment for maybe a week, and a lot of users show up even on the first day. And so the context during that first day may not really reflect very well at all that stationary distribution, right? And even the week might be unusual relative to the stationary distribution. So that's the concern we have in mind.
Thank you.
Yeah, great question.
Dan, I have another question. With the historical data, can you learn this non-stationarity? Like, you're not assuming anything, you're not going to assume anything about it being learnable, but presumably if it had some pattern to it, you could learn it.
Yeah, I mean, that is my my feeling. So we don't treat that carefully. We kind of assume. So yes, we don't treat carefully the problem of learning how much non-stationarity there is. But that's really in the back of our minds, is that kind of in some of these examples, you're going to see it's reflected in the prior distribution. And I imagine that if you run a lot of experiments and have a lot of external data, you could calibrate well that prior distribution to the kinds of non-stationarity you've seen elsewhere in your data. Exactly right. So this segues well, I guess, into
so maybe Dan,
here's
one
an
more
example like what Christine is saying.
Related question. So kind of at a high level, how should we think about relating this or to, like, you know, these works that have these, like, you get a regret bound that has whatever in hindsight the level of non-stationarity was, and is the thought that that was made for not picking the one best arm, but that's kind of heavily tuned to a regret? And should we think about this as like best arm analog of the variation budget work, or is that completely the wrong way to think about it?
Great. I think that we're going to be more like, great. So it's actually a little closer to the best arm analog of not the variation budget work, I think, but just usual non-stochastic bandits. Here, let me talk through this example, and then it actually, I can draw a tighter parallel through this example, I think. So here we go. By allowing, so one apparent difference between our work and other papers that assume kind of some non-stationarity in the environment, it would seem, is that we're assuming non-stationarity is driven by observable contexts. In a lot of cases, I think that's true, that you can kind of see that the users who are arriving are different and their recent usage has been different than you expected from the past. But there's surprising modeling flexibility to capture also kind of latent non-stationarity in the problem through the following trick. We're going to take the context to just encode the time period in which the decision was made and nothing else. And we're going to take that population distribution to be uniform over the contexts that happened throughout the experiment. In that case, the best arm to choose is the arm that was best in hindsight, sort of like what Dave is mentioning, over the life of the experiment. Okay, so here, the average reward of an arm in a given time period, the kind of the expected reward of arm I in period 1 or in period capital T, depends on the time period itself. Now, there's a segment of the multi-arm bandit literature, they call it a non-stochastic formulation of the multi-arm bandit problem, that allows these theta parameters to be completely arbitrary. They're actually picked by an adversary whose goal in existence is to screw you up. Now, I guess I find that to be highly conservative, a little bit, to guard against that form of non-stationarity in the world. And instead, a little bit to Christina's question, what I would like to be able to do is impose some sort of structure on which types of patterns are plausible. Okay. So one way to impose structure under this problem is to model these theta parameters as being drawn from some kind of distribution, and then use the structure of that distribution here, the covariant structure of the prior, to encode what kinds of effects we need to guard against. So here is these plots that I teased at the beginning are one example of doing that. Here I'm taking the parameter drawn at time t to be modeled as an arm-specific effect offset by a common but exogenous time trend. Now, in this sort of model, where there's a very particular structure to the prior, measuring arm 2 in and of itself is not especially meaningful. But if we measure arm 2 and arm 3 close together, then the difference between them is close together in time. Then taking the difference in reward observations is pretty close to measuring the difference in their arm effects. Now, what does close together in time mean? That really depends on how we pick this bandwidth parameter here. All right, so we can capture either models where the world changes very rapidly, and so you need to measure arms very close together, or where the world changes very slowly. Okay, so Dave, I hope that starts to answer your question, that there's some model of non-stationarity here that's common in the literature, and one shift in this, at least in this special instance of the problem, one shift is just that we have a way of imposing structure on the non-stationary.
I guess a question would be, if, you know, at least my understanding of these kind of works that get a regret bound that has in hindsight how much non-stationarity there's been, is that, I mean, it's adversarial in some extreme way, but at the same time, if the adversary has not chosen the context to be all over the place, you will have done better provably. Is that a reasonable question?
I think that okay, papers like Asafzivi's and then that you have in mind, maybe
So like these like hedging the drift, all these kind of like these things. Yeah,
those are relatively different in that what they're trying to do is pick the best arm for each block of time.
Right. Okay. So that's
so
you're going for the one best arm at the end of the day. Is that?
That's right. That's right. So they'll get, t to the 2/3 regret.
Yeah, exactly. This is what I'm thinking.
Yeah. So this is quite different in goal, I think, as well.
Okay. Thank you.
Dan, I have a quick clarification question.
Sure.
So the non-stationarity, I guess this time component only enter the theta t. Does it also enter the, I guess, previously you have a W or omega X, which is basically the composition of the population. Does the time effect affect that composition of population as well?
No, it doesn't. It doesn't. So that's just one distribution. And I'm sort of imagining, if you wanted to think of this like in a stochastic process sense, think of Wx as the limiting accessorial limit or something of the xt process, right? So it doesn't, there's no time trend exactly in that object. But throughout the short period of the experiment, we have some other unusual pattern going on.
I see.
All right. Now I'll try to speed up a little bit. So in all papers that prove theoretical results, I think it's helpful to have in mind, hey, what's the one example that breaks most proofs, breaks most algorithms, and so on. And what I'll tell you here is the example that breaks everything. And I think a nice thing about a lucky thing in this case is that there's some nice interpretation of this problem. So here's the example. Let's imagine that we run a week-long experiment with the goal of deciding which fixed arm to employ across future weeks. So for concreteness, as motivation, let's think of a pricing problem. I am, this is a Toy Story, I'm Apple, and I'm trying to learn how to price laptops. Okay, and I'm gonna run a 1-week experiment where I try to play with the price and see how users respond, see how people respond. Now, they do not want to learn a price to charge on Mondays and a price to charge on Sundays. Because if after the experiment, it turned out that there's always a price drop on Monday, people would then later on respond to that by delaying their purchase until Monday. Okay, so there's incentive compatibility constraints essentially that restrict the space of pricing plans that they want to implement in real life. Okay, so they want to find the best price to employ that would maximize revenue if employed across future weeks, or maximize some notion of profit. The ideal choice is, okay, the ideal choice is the one that is best on average throughout the week, where theta I1 is the average revenue that price I gives you on Monday. Okay, so the contexts here are going to have this unusual pattern. They go Monday, 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 Monday for 1/7 of the users. Then for the next 7th of the users, it's Tuesday, 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 Tuesday. So on. Okay, so in terms of kind of non-stationarity, this is has quite a painful pattern to it, where the contexts at the beginning are really not representative of the average throughout the week. All right. Now we could extend the model we just had of one we had here to now include an interaction effect, where there may be reasons that high prices are just more effective with people showing up on the weekend than they are for the people showing up early in the week. All right, now what's hard about this? There's two things that are really hard. There's one that I kind of knew a priori, which is kind of before starting this project, I guess you know, that if there are these day of week effects and you don't model them, you could be in trouble. So if you run an algorithm thinking the world is IAD, and you actually have this this trend across the week, and then you can be confounded. Now, what I did not see coming is the second challenge, which we'll call information delays. So this is a challenge where if you run an algorithm that does proper inference, it actually accounts for day of week effects when forming beliefs about the effectiveness of different arms in different contexts. That algorithm has a problem that it does not, uncertainty does not resolve until Sunday. Okay. Somehow you cannot fully know whether a price is effective until you see its performance in all contexts. Okay, and I'll show you a formal example of how things break, I guess, with this. So there's one in the paper, but just in your mind, I think maybe you can see at a high level that if the goal was to be adaptive and as adaptive as possible, well, information delays are the enemy of adaptivity, because adaptivity is about getting quick feedback on how effective an action is and adjusting in response. So if there's information delays, it's going directly in the opposite direction. All right. So in the paper, we go through carefully two examples. One shows formally that if you ran an algorithm that just pretends rewards are IAD, ignoring day of week effects, then it really screws up. It can focus in on whatever arm was best on Monday, not gathering enough information about other arms. And as a result, no matter how many people show up throughout the 1 week, no matter how many kind of measurements you get to make, it does not correctly zero in and identify the best one. All right. Now, maybe a little more subtle there's another example in the paper that shows formally that a UCB analog of the Thompson sampling algorithm we propose breaks as well in the same sense. But really the interpretation of it is that it's breaking due to information delays. So what happens to the algorithm is it thinks, hey, this arm might be the best one to employ throughout the week. It has maybe decent expected performance based on my limited knowledge so far. And it has high upside because I have high uncertainty about its performance throughout the week. And so the UCB plays an arm that has high upside. But upon playing it, its uncertainty does not resolve, even if it plays it over and over again, because it has to wait until Sunday to resolve uncertainty. All right, you can't resolve the quality of an arm until all the contexts arrive. So this algorithm gets stuck playing. What happens in this example is the algorithm gets stuck playing maybe only one arm on Monday. And as a result, when you look at the data generated throughout the week, you just can't infer which arm is best. Dave?
I mean, is there a notion of cheating and folding the last L contexts into a history context, and then you kind of, by cheating and blowing up the context space, you kind of do away with the issue because it's implicitly then aware because it's just like the context is whatever the last L contexts were? Is that, maybe that makes no sense.
I don't think it works here because, I mean, fundamentally on Monday, all the last contexts are Monday. Right, so there's no set in which looking back would, I think, help you there. You just need to respond to your uncertainty by measuring a diverse set of things, diverse set of arms. And that's my interpretation. Okay. Let me sort of go through quickly where we're going. So where does this algorithm go? Well, the algorithm is Bayesian. So in some ways, you can think of it as tracking beliefs as time goes on about these latent theta parameters that influence the reward you expect to see from any arm in any given context. But now you can also, though, given you have beliefs about this, think of the algorithm as maintaining beliefs about a particular relevant marginal of that distribution, which is the population level performance of the arm. Okay, so if you compute here this population target vector, xpop, the average performance of an arm throughout the population distribution is this inner product, and we can maintain beliefs on that as well. Yeah, Dave?
Sorry, one other clarification. Maybe I'm confused. Like, is it that the distribution of the context is changing over time, or the actual, what the reward is for a given context is changing over time?
It's that the distribution, is it the context, the distribution of a context is changing.
Okay, but like the actual, what happens when you see a given context, that is not changing over time. That's a fixed.
That's right.
Okay.
That's right. And sort of the only in between where you can kind of like squint and see that they're very similar is just in this case where the context is an indicator of the time group.
Got it. Thank you.
That's right. Okay. So what is our algorithm going to do? Well, it's based on the idea of Thompson sampling. And we're going to make basically two modifications to the way you usually run Thompson sampling. So the usual definition of Thompson sampling in contextual bandits is that you play an arm according to the posterior probability that it is the best arm, the reward maximizing arm, in the current context. What's the chance that this is the arm that maximizes revenue on Monday? So instead, because we're targeting learning a population level decision, we are going to sample arms according to the probability that they are the best arm, i.e. the one that maximizes average reward, if deployed across the population. Okay. So that's the first change, and really the key change is we change what we're doing inference about when we snap. Okay. And there, I'll kind of try to go quickly here. The second change is one that if we're in talks where I've gone a little faster, I mostly omit. This is a change that comes out of an earlier paper of mine. It modifies a little bit how you run Thompson sampling to make it fit settings where your objective is not just to maximize reward earned during the experiment, but to be able to make a good decision at the end of the experiment. Right, so we're really thinking about post-experiment regret as the key objective here. So we're going to make this modification. All right. Now, let me sort of tease what the two main results then in this paper are. It's now we're interested in resolving this tension that I mentioned way at the start of this problem, this tension between efficiency and robustness. Okay. So if you go back, we're going to have two kinds of results. Trying to stress test whether the algorithm is able to attain efficiency through adaptivity, and whether it's able to attain robustness in something like the day of week problem, which requires resilience to these non-stationary contexts. Okay. So this business of proving regret bounds is not perfectly precise. Right, so it's not like dynamic programming where you come up with the objective and you solve for what is exactly the optimal algorithm. Instead, there are different kinds of regimes that seem to stress test different characteristics of the algorithm design. And so to stress test different features of how this algorithm is performing, we're going to come up with two different ways of formulating regret bounds. The one on the left is stress testing robustness in problems where there's an arbitrary delay in observing rewards, this L parameter I briefly mentioned, and where the context sequence is an almost arbitrary sequence of vectors. The one on the right, so this is really stress testing whether the algorithm can perform as well as a randomized control trial in settings where there's almost no hope of doing better than running a randomized control trial. The setting on the right looks more like a conventional Bandit model, where IID contexts allow you to make to infer a lot from the early experience in running the experiment and adapt in response. And so here we'll look for sharp asymptotic efficiency bounds that are problem specific in nature. So to tell you a little more about the sort of punchline here for this part, really it's hard to parse what this bound is in real time. What I'll tell you is it's sort of the same thing you would get if you imagined you ran an RCT. So you sampled arms uniformly at random, providing resilience to all this non-stationarity that's going on. And then you apply the central limit theorem to bound your regret at the end. What you would come up with is almost exactly this. All right. Now, on the right is a best arm identification equivalent to things like the Lie-Robbins efficiency results that you might be used to in standard Bandit. All right, and sort of want to mention that if you were interested in only getting one of these results, it may not be so hard to design an algorithm that matches the result. What is, I think, especially delicate here is coming up with a simple algorithm that does both well, because they are at tension. The easiest way to get the result on the left is just to run an RCT, to not adapt in response to rewards you get early on. But what you want to do to get the result on the right is to adapt as aggressively as possible, to play bad inferior arms just the minimal number of times. And the last thing I'll sort of mention here is that the results are formulated in a fairly different way, at least some length, I guess, in reading the paper. So this one, because we want to stress test how well we perform as a function of the context sequence, we condition on the sequence of context, let it be arbitrary. All right, and we depend only on some function of the time average of the contexts and not their order. This one is Bayesian, so we integrate over the prior. This one is not stress testing the ability to handle arbitrary context sequences, and so it integrates over IID context rows. But we're trying to figure out instead how the algorithm performs when there's different levels of separations between the qualities of arms. And so we condition on the parameter theta and do what I would think of as a frequentist analysis. All right. And just as a sort of teaser, because there's many theoreticians in the audience, if you spend a lot of time in the Bandit literature, you find that there's a lot of different papers, but there's kind of a proof recipe. And you just kind of get used to the way to prove results. This setting was very challenging for us, particularly the robustness result, and required what seems to be a very different proof technique that uses inverse propensity weighting, implicitly analyzing the posterior distribution. So if you're interested in all these different techniques in this area, you might check out this proof in the appendix of the paper. Okay. And I think I'll close here. Now I'm at time. In terms of related work, I don't know anyone who's written down the problem in exactly this way or studied this variant of Thompson sampling. So in some sense, there's nothing that close to what we've done. But I think that philosophically, the closest thing out there are works on non-stochastic best arm identification, which take a more adversarial view to the non-stationarity in the reward sequence that might be coming out in the problem. All right. So thanks everyone for asking so many interesting questions throughout and sticking with me for this whole time.
Okay, great. Thanks, Dan.
Hi, I have a quick question.
Yes.
Hi, this is Lavanya from UIUC. I wanted to check, you said that the efficiency depends on testing the not good arms at least a little bit. Now, wouldn't that be difficult if you had a lot of arms? It could be like the Spotify example, you just have a huge other set to pick from and so on. Or if it were like the Sunday through Monday, Sunday through Saturday example, that would be simpler. But if you had just a very large number of arms, how would that work? Or exponential number of arms even.
Yeah, so I think that it's a great question. In some ways, if you take an algorithm like Thompson sampling or one like UCB, and you specialize them to settings with very few, with a small number of arms and 20 arms or something. There, it's easy to see that the only efficiency gain really that's resulting from them is an ability to quickly rule out the really bad arms, right? You measure them a few times, you stop focusing there. Now, in some ways, the real win out of coming up with the design principles like those is if you code problems where there's a very large set of actions. Maybe it's the set of paths through a graph and you want to find the shortest path. So there's a huge set of arms, but there's structure to the problem. The benefit there is that the information structure to the problem, the fact that different paths, but they overlap, allows you to still zero in on the efficient part of this decision space. The same algorithms work, but the proofs differ. Maybe. Did that make sense? I'm not sure.
Yeah. I mean, if their correlation or structures are overlap, like you said, that does help. Yeah.
Yes.
Okay. Are there any further questions? Okay, Dave, yeah.
So a two-parter, Dan. So,
okay,
which is going to turn into a 406-parter, and then everyone else will probably depart if it's based on the. Okay, so at the end of the horizon,
yeah,
can you roughly tell which of these two situations you were in, or no? Not like throughout, but like you've gotten to the end, you've seen the whole thing play out. Is the high goal for like most of these kind of scenarios that in the end, based on what the context actually were, you can kind of tell, were you in the regime where I should be robust or the regime where I should be aggressive, or is it not clear?
Yeah, I think
where I'll jump the gun, maybe
okay.
the part B, as your answer is, the part B is going to be, if you could tell, could you just play both algorithms in like randomly alternating periods or something, and then just which of these things is. I'm just trying to conceptualize. You don't care for the regret accumulated over the horizon. You just care for the good decision at the end. What would stop a naive approach like that, where you kind of, you randomly do both in some reasonable way and then do whichever you think is appropriate once you get to the end?
Got it. So, I mean, I think that you would still, you still would not get the sharpness of these asymptotic optimality results if you just flipped coins to decide, sometimes use uniform and sometimes use
Well, why would it be off by like more than a factor of 2 or something? I mean, why is so
I think it would be off by a factor of 2. I think you're right.
Unless it really, because I guess your choice of which arm you pull doesn't affect the context going forward, right?
Got it. So I think that this goes back a little bit to this question of, hey, was it off only by a factor of 2? I have to think about that. But this goes back a little bit to this issue of, okay, if you have 7 arms, there's maybe many ways to resolve this problem. But if you want to salvage adaptive algorithms that seem to be critical in places where the decision space is larger, how would you do it? So that's one part of my motivations. I don't want to do that. There are versions of this result that, so yeah, to reformulate this question as a one-parter, you could basically say, why not just do 50% uniform and 50% Thompson sampling, right?
Where it would have to be randomized, because it couldn't be that you miss every Monday or something like that, right? Or something, I guess, right? So,
yeah. So one thing is like kind of, I'm looking for a more elegant and fundamental way of resolving the problem that works more broadly. That's one part of it. Now, if you were to, I mean, Chow, who I think is now on the call and I've been talking about, you can also analyze the regret of these algorithms in this experiment and prove results about that and so on. And there, I think you would I mean, almost using exactly our techniques. And there, you might come up with a more fundamental, or more appealing measure of what is lost by mixing in the uniform exploration. And I think the last bit is if the set of arms is large and there was correlation structure, then mixing in uniform doesn't resolve it. Now, there's a question of whether our algorithm resolves problems where there's, I'm being a little hand wavy that just because Thompson sampling in usual environments works with correlated arms, where you can't explore each arm. Does this? Being hand wavy, I think so.
Okay, no, that makes sense. And then,
is there a four-parter?
Well, this is then now.
Why don't we go offline if there's going to be further? Let's just do that.
Are there other questions?
But, yeah, if anybody else has a question before we do that. Okay, fine. Well, we can still ask Dan questions, but I'll stop the recording and everything. Okay, so thanks again, Dan. People are welcome to stay as well, obviously.